ay plus b I cap plus ax j cap, where a and b are dimensional constants. These are given in terms of some numbers, we are not going into that. You have to find out the fluid rotation and the stream function. Again this is a very simple case to talk about, but whenever we are trying to understand the fluid rotation, we will now try to understand a very important concept which is asked in this particular problem, that is what is the circulation about the curve. We will now learn what is the meaning of circulation about a curve bounded by the following lines. What are the lines? Y equal to 0, x equal to 1, then y equal to 1 and x equal to 0. So we have come across a new terminology in this problem called as circulation. So we will keep this problem a bit aside, try to learn what is the meaning of the terminology circulation, and then we will try to apply it. The terminology circulation is not a very new terminology, it is very much related to what we have already learned. So and we will see that it is very much related to the concept of vorticity. How it is related to that? Let us say that we have a line, a closed contour, a contour which is closed by some curve. Now if you take a small line element located on the contour, let us say that we take a line element like this. So you may have a velocity vector, say v, and you may assign a vector to this line element by giving it a directionality. Say you are traversing along a clockwise direction or an anti-clockwise direction. Here we are traversing along an anti-clockwise direction. So if you find out the v dot dl, the dot product of the velocity vector with this one, and find the contour integral, that is the integral of this over this closed path by traversing in a particular direction, that is known as circulation along the curve, which is given by a symbol capital gamma. This is circulation. Now it is possible to express this in terms of an area integral by using the Stokes theorem in vector calculus. So you can express this in terms of curl f, or here the curl v, where the vector function f is here v, where S is an element of the surface, ds is an element of the surface, and S is the total surface that is bounded by this closed curve. That is very, very important. So you can clearly see that if you talk about the value in a plane, it is possible to make out from this that first observation is this is nothing but the vorticity vector. So this vorticity vector, when you utilize this vorticity vector here, so the circulation is nothing but, how you express it in terms of vorticity? It is just like roughly vorticity per unit area, or it is in the other way, it is like vorticity into the area is the circulation. So it's just the other way, not vorticity per unit area, but vorticity into area is the circulation. So let us take an example before going into this particular mathematical form to figure out that how you can calculate what is the circulation. Now to do that let us take an example which is not the same example, but we will utilize what we learned from that example to solve this problem. Say you have another example where you have the velocity components given by polar coordinates, say v theta is equal to omega r and Vr equal to 0, there is no Vz, a 2-dimensional flow. Okay. Let us say that we want to find out what is the circulation around a closed contour. So a closed contour in a element in a polar coordinate form you can generate in this way. So you consider that at a distance r, I am magnifying dr to show that as if dr is greater than r, but it is just for clearly drawing the figure of dr, and this angle say is d theta. So what is the contour that we have chosen? We have chosen the contour which is formed by this element in the polar coordinate. So this like A, B, C, D. Now we are interested to find out the circulation. So we start the traversal from the point A. So what is the V theta defined? V theta is defined as omega r. So we are going from A to B in this direction. What is V dot dl? Here dl is also along AB, because it is a small arc, it is almost like tangent to the curve. V theta is also tangent to the curve. So but the thing is your positive theta direction is anti-clockwise. So V theta and dl, so V theta is in the opposite direction as that of your dl if you are trying to traverse the path in this way. So when you go from A to B, V theta is opposite to that of your dl that is drawn. So V theta dot dl will give a minus sign. What is the magnitude of V theta dot dl? So for AB, V theta dot dl will be omega r into r d theta with a minus sign. So what we are writing here is V theta V dot dl. Okay. Then for BC, V theta is along the tangential direction, BC is along the normal direction, so their dot product is 0. So this does not come into the picture, it is 0. For CD, what is V theta? So for CD, what is dl? The dl is from C to D, you are traversing it in a particular direction, so you are traversing it like this. For CD, what is V theta? Omega into r plus dr. And what is dl? That is r plus dr into d theta. Okay. And for dA, it will be 0 just like before. So when you sum it up, this contour integral will be the sum of these 4 line integrals. So sum of these 4 line integrals will give what is the total circulation, that is sum of these. So what will be that? You see the first term minus omega r into r d theta will be cancelled with 1 omega plus omega r into r d theta. Then there will be terms omega dr r d theta, there will be term omega into dr square d theta. Then any more term? So one of the terms this has got cancelled with omega r into r d theta, then omega r into dr d theta we have written, then omega r into dr d theta, so another omega r into dr d theta, right. So 2 omega r dr d theta. So if you find out what is the circulation per unit area, what is the circulation per unit area? This divided by r d theta dr, that is dA. The dA of this shaded one is r d theta dr. So that is nothing but 2 omega. Actually this omega is the angular velocity and 2 into that is the vorticity. So this is like the vorticity. So what we get from here, this is an example of illustration of the same concept. This is just from a vector calculus theorem, this is just detailed illustration of that. So you can conclude from this that in such a case you can find out the circulation per unit area equal to vorticity. So from that you can relate vorticity with circulation. So if you find out one, you can automatically find out the other. This type of example where you have v theta equal to is proportional to r and Vr equal to 0, this is known as a forced vortex. So it is something like you are creating a rigid body type of rotation in a flow by having an angular velocity to the system. So it is an example is like we have discussed in the class earlier, that you have a cylindrical tank and you start rotating the cylindrical tank, in the limit as you are neglecting the viscosity, it takes the shape of a paraboloid of revolution type. That is an example of a forced vortex. So you can have a forced vortex with this type of velocity. So the velocity is 0 at r equal to 0. You have to keep in mind one very important thing. So the circulation per unit area is given by the vorticity. Let us say that somebody has taken an area like this. So this is a circle, somebody has taken an area like this. This is the center of the circle and is trying to find out what is the circulation. We will see that in certain cases this definition will be restricted if we include the origin. So let us take another example that will illustrate that what is the corresponding problem. So take an example 2. With understanding of example 1 and example 2, this example problem that we are going to solve, it will be easy for us to appreciate. Example 2 is something which we call as free vortex. What is a free vortex? So free vortex is defined as the v theta component is inversely proportional to the radius. Here it is directly proportional to the radius, it is inversely proportional to the radius, and Vr is equal to 0. So this kind of a situation you get in a kitchen sink. So you open the tap and what you will see that as it comes, so the sink is first, say you fill up the sink first with water, close the valve so that the water cannot go out. Now suddenly open the valve, you will see that as the water comes to the outlet and goes through the pipe, when it comes to the center of the sink, it is coming out with a very high velocity. So there, and it has a sense of rotationality in the flow, so the v theta is inversely proportional to the radius. It is singular at r equal to 0 mathematically, because at r equal to 0 it is as if v theta tends to infinity and you cannot have an infinite velocity. So you have to keep in mind that this is something where this r is defined in the limit as r tends to 0 plus, not r equal to 0. R equal to 0 is a point of singularity for such a case. So when you are writing, now you try to figure out that what should be the circulation. So the circulation here, just we will have similar element AB, BC, CD, DA, we will straight away write because by now you know how to write it. So for AB what will be the circulation? So minus c by r into r d theta, for BC it is 0, for CD plus c by r plus dr, because nu r is now r plus dr into r plus dr d theta, and for dA it is 0. So very simple observation is this r fx will get cancelled out, so it is 0. Okay, and clearly it is so because you can also find out the vorticity, you will find that the vorticity is also here 0. These types of cases where the vorticity is 0 is known as irrotational flow. So irrotational flow is a flow with 0 vorticity. We will come into the concept of irrotational flow soon. Irrotational flow means 0 or null vorticity vector. That is the very simple definition, and from the name itself it is quite clear that there is no element of rotationality in the flow, that is why it is called as irrotational flow. Now if in this example you take a closed contour like this by definition is a closed contour, you try to find out what is the circulation. So for these two edges the circulation will not be there, for this edge the circulation will be there, and clearly when you sum it up over the contour it is not 0 if you take such an element. What is wrong with that? A very important conceptual mistake is there by choosing this element. You have taken the element by including the point of singularity. So you cannot take an element which contains the point of singularity to establish the relationship between the circulation and the vorticity. So obviously this is not a valid element. Yes.
In the case of this free vortex,
yes,
we come out with the vorticity is equal to 0, that is there is no rotational.
yes.
So but as we see, you told in the example that water it circulates while going down the thing.
No, that is I mean that is like it is just coming with it is not a circulation. It is like when you will always see that when it comes, we will see now that practical example, when r equal to 0 it is not defined, so it is always a forced vortex close to r equal to 0. So what is the practical case? The practical case is never for purely forced vortex or a purely free vortex. So the practical case, if you draw the velocity profile v theta versus r, you know that at r equal to 0 if you use a completely free vortex understanding then v theta will be undefined. So actually always very close to r equal to 0 it is a forced vortex. So close to r equal to 0 v theta will be equal to omega r, so it will be something like this, and away from that it may become a forced vortex, a free vortex. So it is like a rectangular hyperbola type.
But then there is a rotation.
There is a rotation close to this one, so this is known as this is the practical example. Free vortex or forced vortex, neither of these are like very practical examples, but their combinations are quite practical. This is known as Rankine vortex. So it is a combination of free and forced vortex. So up to a particular radius, say critical radius, it is like a forced vortex. Beyond that it is like a free vortex. A very classical example that occurs in nature is a tornado. So a tornado, very close to the eye of the tornado, it is up to that it is a forced vortex, so it has a strong element of rotationality. Beyond that it is like a free vortex. So a tornado may be very well approximated by a Rankine vortex, which is a combination of free and forced vortex. You have to keep in mind that if you have such a combination, you have to satisfy that at this point, at this critical radius, I mean where you have like a transition of behavior from free to forced vortex, the v theta should be same as given by the considerations of free and forced vortex, because you cannot have a discontinuous velocity field. The velocity field in the physical sense is continuous. Now if we come to this example, we will try to utilize this example to find out the circulation. So first, what is the rotation? So the rotation is given by the first you find out the curl of the velocity vector. So it is a two dimensional field. So the curl of the velocity vector eventually will boil down to that you want to find out the angular velocity in the xy plane. So what is that? half of this one. So, this is basically if you find out half of the curl of the velocity vector and take its component in this plane wherever it is important, it will also boil down to the same expression. So, that will be a minus a, that is 0. The rotation is 0, that means its vorticity is 0, and by the relationship between circulation and vorticity, now you have a curve bounded by what, y equal to 0 and 1 and x equal to 0 and 1. So, it is like a rectangular contour. This is x equal to 0, this is x equal to 1, this is y equal to 0, this is y equal to 1. So, this is the contour, this is the area bounding the contour. So, this does not include any point of singularity. So, this is a valid area, and therefore, the circulation about this curve is expressed in terms of the vorticity. Since the vorticity is 0, this is also 0, you need not work it out, but I would suggest that you work it out yourself and check just by following this that you are getting 0. That will be a good exercise for you. And the stream function, we already know how to do it, I am not going into the details of it. The whole purpose of this problem was to demonstrate the rotation and the circulation part. Next we will go to a concept that is very much related to the rotationality of the flow again, and that concept is given by the name of velocity potential. So, we will see that what is the velocity potential and what are the important considerations that go behind this. So, velocity potential. Let us consider the case of irrotational flow. So, this is defined only for irrotational flow. So, for nothing else, therefore, we must find out the condition for irrotationality. So, what is the condition for irrotationality? The curl of the velocity vector is a null vector. So, what it will boil down to? So, if you write the 3 scalar components of this by expanding in a determinant form and equate the scalar components to 0, you will get this. So, from this you can see that if you now parameterize, say u equal to and w equal to del phi del z, where phi is a function, it is in general a function of x, y, z, then this definition automatically satisfies these requirements. Automatically satisfies these requirements. This is not a magic, this is very much obvious, because from the theory of vector fields you know that if the curl of a vector is a null vector, then that vector may be represented as the gradient of a scalar function. So, if the curl is 0, it is a null vector, it is possible to express V as a gradient of a scalar function phi. So, that is what, which is the mathematical basis of such a coincidence. It is not a coincidence, but directly it follows from a important vector identity. Now, such a field where the curl of the field is null vector, the field what we talk about is a general vector field, here it is a velocity vector field, we call it as a conservative velocity field. So, in general in field theory, if the curl of a particular vector field is a null vector, then that field is a conservative field, it may be expressed in the form of gradient of a scalar potential, maybe with plus or minus sign, but it is all the same, because again with minus or plus this will be 0. So when you express the vector field as a gradient of a scalar potential, what is the significance? Think about the case of a gravitational field. So when you say are having a displacement of a particle from 1 to 2 in a gravitational field, it does not matter whether you are going by path this or this, provided only gravitational only gravity is the important force. Then the work done for going from 1 to 2 is independent of the path and just is dependent on the difference in the potential, that is the potential energy in this case. So that path dependence comes from the conservative nature of the field. So in a conservative field, so similarly this is talking about a conservative velocity field, not a conservative force field, but the concept is very much analogous. So whenever you have such a conservative field, the field is expressible in form of gradient of a potential. In such particle mechanics in a gravitational field, that potential is a potential energy that we know. So here we are talking about a velocity potential. So now we are interested say about a relationship between the velocity potential and the stream function. Now when we are interested about a relationship, they must be comparable. So when, under what case, under what circumstances they are comparable. So what is our objective now? Objective is to find out a relationship between stream function and the velocity potential. So what type of flow should we consider? Consider what? So we should consider a case when both are defined. So when is stream function defined? It is defined for 2-dimensional incompressible flow, need not be steady, 2-dimensional incompressible flow, when the velocity potential is defined for irrotational flow. So it has to be 2-dimensional plus incompressible plus irrotational, so that both phi and psi functions are defined. On this basis we want to compare the two. So when you are considering a 2-dimensional irrotational flow, you have only the relevant components as these u and v. So now let us find out what is, say, how we can express d phi exactly in the same way in which we express d psi. So what is d phi? D phi is this one. So it is u dx plus v dy, because u is defined as the partial derivative of phi with respect to x and so on. Now if you have a line of phi equal to constant, just like we had psi equal to constant, then that will mean d phi equal to 0. That means for that line which is having phi equal to constant, you can have dy dx for phi equal to constant is equal to minus u by v. Let us now recall what was the case with the line of psi equal to constant. So psi equal to constant, so what was the expression for d psi? So what was d psi? V dx minus u dy. So what is dy dx along a line with psi equal to constant, that is d psi equal to 0, that is equal to v by u. Now if at a common x comma y, if we want to find out the product of this dy dx for phi equal to constant and dy dx for psi equal to constant, what is that? That is u by v, sorry, minus u by v into v by u. Okay. It is not trivially minus 1, that is a very important thing, because who has guaranteed that u and v are non-zero? If at least one of these components you have 0, then you get division by 0. So you have to make sure that these are non-zero. So if these are non-zero, then only you may cancel out this, and when you are cancelling out both, you are ensuring that u v both are non-zero because both appear in the denominator. So then in that case this is -1, and what does this -1 signify? That if you have a line of constant psi and if you have a line of constant phi, they are orthogonal to each other. So you have phi equal to constant and psi equal to constant. So we do not say that they are perpendicular because it is not that the curves are perpendicular, but they are common tangents at the point, at the common point. So here you have a tangent like this and here you have a tangent like this. So these are perpendicular to each other, and therefore the important conclusion is that phi equal to constant lines which are called as equipotential lines. So this is equipotential line. So this is very much analogous to the equipotential line that you get in say electromagnetic field theory. So the phi equal to constant and psi equal to constant, these lines are orthogonal to each other everywhere in the flow field except for certain points. Which are the points? The points are where the velocities are 0. Those points are known as stagnation points. So in a flow field, the points where the velocities are 0, those are called as stagnation points. So stagnation point is a point where v is 0, and at the stagnation point you do not have such a relationship because at a stagnation point you cannot really work out this. So it is not true that the streamlines and equipotential lines are orthogonal everywhere in the flow field. They are orthogonal at each and every point except for the stagnation point where it is not defined in that way. Now finally what we will see a relationship or a governing equation for the expressions for phi and psi. So if you say that you are interested about this case when you have both 2-dimensional incompressible and irrotational flow. So when you have a 2-dimensional incompressible flow, so you have say irrotational flow, you have u equal to this and v equal to this. Now if you want to satisfy this with the continuity equation, continuity also has to be satisfied. So you have this equal to 0. That means you can write or Laplacian operator of phi equal to 0. Similarly, if you start with the definition of the stream function, you have u equal to and v equal to minus this one. Now this automatically satisfies continuity, but for the case when you are considering both phi and psi are defined, it also has to satisfy the irrotationality constraint. So for irrotationality you must have this equal to 0, okay. So for irrotational flow, now if you substitute this, you will get the same thing, just replace phi with psi. So you get Laplacian of psi equal to 0. So you can see that for 2-dimensional incompressible and irrotational flow, both phi and psi satisfy the Laplace equation. This prototype equation, Laplacian of phi, that is the del square of phi equal to 0 or del square of psi equal to 0, the general prototype is del square of something equal to 0, that is known as Laplace equation. So both phi and psi satisfy the Laplace equation. It does not mean that their solutions are same because boundary conditions are different. Although governing equations for phi and psi are the same, but their boundary conditions are different and therefore solutions are different. So in summary what we can see, that we have defined what is the stream function, we have defined what is the velocity potential, we have seen that there is a relationship between these two when we have both defined, that is 2-dimensional incompressible irrotational flow, and both in terms of their governing equations and also in terms of their orthogonality. Now what we will do finally, we will look into some visual demonstration of certain types of flows and end up the discussion today. So in these visual demonstrations we will see some examples. So first you see this is a shear deformation. See, there is a line element which is marked and this is a flow between two concentric cylinders. We have seen such a case when we are discussing about viscosity. So you can clearly see that the fluid element is deforming. So from a rectangular shape the fluid element is coming to the deformed shape. So this is the angular deformation that we are talking about. We just play it again so that you can see it again. So originally it was rectangular, but because of the shear you see that how it is getting deformed. Okay. Now we will look into a second example after this where we will see that like if you have a general case when a fluid element is moving along a path, then like it can have a general type of behavior, so it can have deformation. So here it is just rotating, you see that it is not deforming, so it is just a pure rotation. Now let us look into a third example where we see a flow. This is a very interesting case. This is a case when it does not have any type of angular motion, angular deformation, neither shear deformation nor rotation. So it is as if just it is getting stretched. So I will leave it to you on as an exercise. You find out what are the velocity components u and v that will lead to this condition. What are the important restrictions? You must have both the partial derivative of u with respect to y and partial derivative of v with respect to x equal to 0. Then both the angular velocity as well as the angular deformation will be equal to 0, and then such a case is visible, that is known as a stagnation point flow. Finally let us look into a general case of an incompressible fluid element, how these fluid elements flow. So this is a visual demonstration of the continuity equation. So you see that whatever flow is entering, the same flow is leaving. So if you have a constrained passage, what is happening? What is happening is that the velocities are increasing to compensate for the decrease in the cross section area. So this is what like A1 U1 equal to A2 U2, that type of expression that we have seen. So we stop here today. Thank you very much.